Okay, our objective for today, I can solve and graph linear functions. Read together, 1, 2, 3. I can solve and graph linear functions. So we've been doing some graphing, we've been doing some evaluating stuff for some other functions, but today we're going to focus on linear functions. So what are linear functions? Linear functions are a relation that assigns exactly one output value for each input value. It has to be in two variables and has a constant rate of slope. A constant rate of change known as slope. Examples. Here's a set of points. Write those down. And I'm going to give you 3 equations, and then we'll talk about those in a little bit. So copy that. All right. So we're looking at linear functions. And once again, the definition, a relation that assigns exactly one output value for each input value in two variables and has a constant rate of change known as slope. Now, what's different from last week to this week? We'll look up. Last week, I only gave you relations and what? Functions. So if that's true, then that means within this definition should be the definition of function that we did last week. Let's see. A relation that assigns exactly one output value for each input value in two variables. Is that familiar? Does that sound familiar? Yes, we covered that last week. However, for today, since now we have a new term in there, which is linear functions, now we add a little bit more to the definition. What's the one thing that we add? That it needs to have a what? A constant rate of change. Now, what does that mean? Constant rate of change, that it doesn't break a pattern. It's always linear. And you're saying, what does that mean? If we were to graph it, look what it makes. Look up. It makes a straight line. That's why it's within the linear term, there's a word, what? Line. It's a straight line. Okay? So, aside from that, let's look at this relation. And by now you can tell if this is a function or not. Is that correct? Tell your neighbor if this is a function or not. Now, it is a function because it's in the examples, but tell them why it is a function. For every input, there's an output. There's exactly one output, and we saw that which one repeated? -2 of x, but do they have the same output? Yes, that's why it is a function, okay? Next, it says it has to be in two variables. So let's look at the equations given. This one is y equals 2/3 x minus 23. Okay, do you see two variables? Yes. How about this one? Yes. How about this one? You're like, well, yeah, because last week I said that instead of y, what do we substitute sometimes? F of x to indicate that it is a function. Does that make sense? All right, so now that we covered what they are, let me show you what they are not. I'm going to zoom in. Look at those. Oh. And I'll pause it so I can move this. Oh, no, that's fine. So we have this relation, we have this graph, we have this equation, this equation. Copy those, and I'll go over those as to why those are not linear functions. Copy that. All right. First of all, the first relation. Tell your neighbor why this is not a function, please. Let's see, Ryan, why is that one not a function? There's two -2's of x, but they don't have the same output. This one is 3 and this one is 7. That is correct. That's why it's not a function. Now, what did we say about the examples that I showed you over here, that these make a straight what? Line. Okay, look at this graph. Obviously, this is not a function because it's not a straight what? It's a rhombus, and a rhombus has a bunch of different lines or line segments. That's why that's not a function. Another way of testing, of course, last week I said, look at my scanner. I'm going to scan it from left to right. Is that straight? Right there? On the scanner from left to right, if it touches at more than one spot on the graph, touching here and here. So since it's touching at more than one spot, that's why it's not a function. You guys remember that? Yes, Mr. Hugh. All right. Now let me show you why these are not functions. Look up. Let me show you the graph of these. Look at this one. The graph for this one, I'm going to do that in blue, looks like this. And the graph for this one, I'm going to do in red right here. Tell your neighbor why those are not linear functions. Because they're not straight lines. Is that correct? Now, if I was to ask you without the graph, how can you tell if these are not linear functions? Look at these. And look at these. Look at these. And look at those. Talk it over to your neighbor. Tell them why. Other than that. All right. Julian, why? Exponent? Because they have an exponent on the x variable. That is correct. That's why they're not linear functions. All right. So, with that said, let's get some hashtags. What makes linear functions linear functions? Hashtag, hashtag. Share a hashtag with your neighbor, please. One hashtag with your neighbor. Let's see, Ninel, get us started. Bam. Hashtag straight line. Pass someone. Bree. Hashtag one output for each input. Okay? Pass someone. Julie.
Hashtag no curly lines. I mean lines.
Hashtag no curly right?
I mean lines.
Lines. That's correct. No curves, right? All right. What would be one last thing? Look at the definition. What would be one last thing we can add to the hashtag? Marissa? No exponents. How about hashtag two variables? Okay. Steps. Oops, sorry. We got 4 steps. Write these down, please. Step 1, write a rule for the function. Step 2, graph the function, which means to do what? Solve for y and use an input-output table. That's for graphing. Step 3, test your graph to see if it's a function. And step 4, evaluate the function after writing the function notation. Copy that. Once again, 4 steps. Step 1, write a rule for the function. That's if they don't give us a function. Step 2, graph the function, solve for y, and use an input-output table. Now, the first one, write a function, a rule for the function, because sometimes they're going to give us a word problem, and they ask us to write an equation for it. Have we been doing that in the past semester? Have we been given word problems and writing equations from the word problems? Yes, same thing, except for you write it in the function notation, or you can write it in y equals to whatever. Step 2, we're going to start right now with an example for step 2, which means to graph the function. But look at the 2 steps specifically within step 2. What are 2 things that we need to do? Solve for y and make an input-output table. So what are the 2 steps that are imperative? Solve for y and write an input-output table. Okay? From there, we're going to test our graph to see if it's a function. We can do that. We know how to use our scanner from left to right, or we can tell by looking at the points. to see if any of them repeat. And the last one, evaluate the function after writing in function notation, and I'll show you how to do that. So let's go with example 1A. So get your graph in front of you. We're going to start with the top left. On the top left of your graph, I want you to write example 1A way at the top. And don't copy this, but let me show you really quick what a linear function looks like. Look up, look at this graph. Does this look like a straight line? Yes, an example of that is, it says, many stretches on the German Autobahn have a speed limit of 120 kilometers per hour. If a car travels continuously, this speed, y equals 120x, gives the number of kilometers in y that the car should travel in x hours. Now check this out. It says here, what is the keyword here? Continuously. That means that there is no break in between. It goes constantly all the way through. That's what's the linear function. All right, copy this one on your graph paper at the top. It says example 1A, and it says graph y equals 2x plus 1. That's one part. And then from there it says tell whether it represents a function. Once again, example 1A, you're writing it at the top of your graph paper, and it says graph y equals 2x plus 1, and tell whether it represents a function. So let me get my coordinate plane over here. We're going to do this one together. So, according to step 2, what are the two things that we need to check for, Isaac? Solve for y. So that's the first thing. So let's look at this equation or this function. Let me zoom in. Is it already solved for y? I couldn't hear a sure thing. Once again, tell your neighbor if this one's solved for y. Yes, because if you write down your line down the equal sign, is the y by itself? Yes, it's solved for y. Okay, so we got that. So what is the second thing that we need to do? Tell your neighbor, please. Use an input-output table. So on the side over here of your graph, you're going to write x, y. And for the domain from now, instead of starting at 0, I want you to start at -2, -1, 0, 1, and 2. All right? So do we know what to do with these values in this equation? Yes. So we substitute the first value as what? -2. So I write y equals 2 instead of x. What do I write? -2. So we're going to multiply times -2 plus 1. Y equals, what is 2 times -2? -4 plus 1. And what is -4 plus 1? -3. That goes right there. I'm going to do the next one in blue, which is -1. So I'm going to write y equals 2 times -1 plus 1. Y equals, what is 2 times -1? -2 plus 1. What is -2 plus 1? -1. That goes right there. I'll do the next one in green. What's my next value? 0. Y equals 2 times 0 plus 1. Y equals 0 plus 1, which is 1. Okay, let me stop you what you're doing right now. Writing utensils down, look up to the screen. Writing utensils down, look up to the screen. All right, here it goes. So, process. What did we do? To graph, we checked to see if it was solved for y. Was it solved for y? Yes. Next, we build an input-output table with a domain from -2 all the way to 2. Are we there so far? We started substituting values to get our y values. Are we there so far? Now, check this out. Since I'm such a nice teacher, and I'm going to ask you to do the work for the first 3 outputs. What does that mean, Mr. Q? Well, if you can see that there's a pattern, you don't have to do the work for the last two. Just fill in the pattern. However, if you don't see it, guess what? You have to do the work. So look at it. Talk to your neighbor, see if there's a pattern from here to here, from here to here, from here to here. Hands if you saw it. Who saw that it's plus 2? Yeah, what is negative 3 plus 2? Negative 1. What is negative 1 plus 2? 1. What is 1 plus 2? 3 and 5. That's what I'm saying. I am going to ask you to do the work for 3, but if you see the pattern, you can fill in the rest by yourself without doing the work. Does that make sense? However, if you don't see it, guess what? Yay! All right, let's graph this. Here we go. Negative 2, negative 3. Negative 2, negative 3. Negative 1, negative 1. 0, 1. 1, 3. And 2, 5. Get your index card. Get your straight line going through those points. All right? By looking at it, is it a straight line? So therefore, is this a function, a linear function? Yes, we can check both ways. We can check to see if any x values repeat, or we can scan it from left to right and see if our pencil touches more than one point. It doesn't, so therefore this is, yes, a function. Fairly simple? Yeah, right? Yes, Mr. Q. All right. Let me go to example 1b. Writing utensils down, look up to the screen. They give us this equation and they want us to graph it. So you know the first thing that we need to make sure this equation has. Everyone, it has to be solved for y. It needs to read something like this, y equal to something. So if that's true and we need to leave this by itself, we need to do what? Subtract 15x, subtract 15x. We're left with 3y equals negative 15x plus 9 divided by 3. We're left with y equals, what is negative 15 divided by 3? Negative 5x. What is 9 divided by 3? Positive 3. Is it in y form now? Yes. What would be the next step? Build a table. Negative 2, negative 1, 0, 1, 2. Do we know what to do with that? Yes. Graph it and check to see if it's function. You don't need to copy this. I'm just going over this. Are we there so far? All right. I wanted to get to this one. Copy this one. Example 2a. Copy this on your Cornell note paper. In the back, hopefully. Example 2a says, write x equals 2y plus 4 in standard form and give the values of a, b, and c. Write x equals 2y plus 4 in standard form and give the values of a, b, and c. Now, some of you have seen this word standard form before, or this term, but for linear functions, it's different. How is that different? Because it should look like this. ax plus by equals c. It looks different from what we've been covering with polynomials because now we are in linear functions. So standard form should look how? Ax plus by equals c. So I'm going to do this one. And I'm going to take the equation given. The equation given is x equals 2y plus 4. Question. Does this equation look like this one? Almost. What do you notice different from this one to this one? That both x and y are on the same side of the equation. Do you guys see that? Focus, please, or you're going to miss it, please. Both need to be on the same side. So what do I need to do to y here? Subtract y, subtract y. That leaves me with x minus 2y equals 4. Do I have both x and y on the same side? Yes. So now that this is what? Standard form. So now they want us to identify what? The values of a, b, and c. A, b, and c. All right, let's look at this equation. Look up and look at our standard form. Say neighbor the value of a. I heard someone, no, I heard someone say 1. What's the invisible number here in front of the x? 1, because here the a is in front of the x, right? So tell your neighbor the value of b. -2, that is correct, because it's in front of the y right there. So what is c, everyone? 4. And that's it. What are the 2 things that they ask us to do? Write it in standard form. There it is. And identify A, B, and C. Do we have that? Yes. So once again, just remember that both variables, x and y, need to be on the same side in order for it to be standard form. So let's look at this next one. Look up. They give us y equals 5x minus 9. Is that in standard form? No, I need to move the x, don't I? Minus 5x minus 5x. Standard form is negative 5x plus y equals negative 9. Is that standard form? Yes, ax plus by equals c. So therefore, what is a, everyone? What is b? And what is c? Negative 9. We got it, yes? All right. Now I'm going to example 3. Look at this one. Let me do this one first, and then you'll copy at the end. It says, without graphing, tell whether this point is on the graph. You're like, without graphing? Think about it. They only give me the equation and the point. What can I do to check if it's on the graph without graphing? You got it. Luca. Close. What values do they give us here? Which is what? X and... So what do? Substitute and see if it's true. So watch. What is 2 times 3 plus 5 times 2 equals 16? Let's see. This is 6 plus 10 equals 16. What is 6 plus 10? Is 16 equal to 16? So therefore, yes, on the graph. Copy this one, please. This was example 4A. Yeah. So just copy the equation and the point, and then the word. Hopefully for tonight is play sheet 5.1. So make sure you grab one on your way out. It's over here. There is tutoring. If I don't see you guys, have a good one. See you guys tomorrow. Bye. And tomorrow we're going to continue with this. We have something else to finish in regards to that, and then we'll move on. Bye.